Welcome to next lecture. In the previous lecture, we just started power electronic converter analysis and we have defined what are various converter circuits in the syllabus of various exams. After that, we started rectifier analysis. And by the end of the lecture, we discussed about single phase half wave uncontrolled rectifier with resistive load. Now, let us take another load, that is pure inductive load. Just for reference, I have drawn the circuit diagram and just a waveform reference lines. Before starting, I will suggest you to pause the video and draw all of these waveform lines. Now here, circuit is the same. Only the difference from the previous is a load. Here, the source voltage Vs is equal to Vm sin omega t as earlier. The source terminals, we have given the name A and B in the previous lecture. Let us follow in the same notation. Load side, the terminal names are X and Y. Output voltage is measured between the terminals X and Y. Load is pure inductor and the load current is denoted with the symbol I0. Voltage across this diode can be represented with the symbol Vd. Now, in this circuit again, the source voltage is pure sinusoidal. Therefore, this is what a sinusoidal voltage waveform. If we give this source voltage to the rectifier circuit just like earlier, 0 to pi, source voltage is positive and hence diode will be forward biased. Diode is an uncontrolled device. Whenever it is forward biased, it will immediately start conduction. Therefore, during its on state, voltage drop across the diode will be 0. Then what will happen? Load terminal X will be connected to the source terminal A. Therefore, voltage across this pure inductor will be just same as the source voltage. Therefore, 0 to pi, the entire positive half cycle of the source voltage will appear across the load voltage. Will appear across the load, where source voltage peak value is Vm. Similarly, 0 to pi, output voltage peak value is also same as that of source voltage peak value. After this, in order to draw output current waveform, output current waveform, we should look into what is the equation for that. Now, in case of resistive load, what was the equation we have? Vm by R multiplied with sin omega t. Now, in this particular case, whether we will get the same equation or not, let us see. Suppose when diode is turned on, what is the equation? When diode is turned on, we can say that the load inductor, pure inductor, is connected to sinusoidal source. Therefore, how can you express the circuit equation? L into di0 by dt is equal to Vm sin omega t. Therefore, from this particular equation, we can write di0 by dt is equal to Vm by L sin omega t. Now, we are interested in expression for current. Therefore, what we can do here, di0 is equal to Vm by L sin omega t into dt. Now, in order to get the expression for I0, let us integrate on both sides. Therefore, left hand side we can have I naught, right hand side Vm by L integration of sin omega t is minus cos omega t. As integration is with respect to t, left hand side I can write omega, denominator I can write omega plus integration constant k. Now how can you find this integration constant k value? By applying initial conditions. What is initial condition? Okay, so you can say that whenever diode is turned on, okay, let us look into the circuit again. Whenever the diode is turned on, this inductor is connected to sinusoidal source. Therefore, we can say that output current will start from 0 whenever this diode is turned on. For example, in this circuit it is not there. For example, if I take one switch here, in that case, when the diode will turn on, the instant when that switch is closed. Of course, in this circuit it is not the case. If at all it is there, you can treat that could be the initial condition. Suppose later analysis will consider that switch. Instead of switch, this diode is replaced with SCR, for example. SCR will turn on at the instant when it is triggered with a suitable gate current pulse. Therefore, the point here is initial condition. How can you write? I naught is equal to 0 at the instant where this inductor is connected to sinusoidal voltage source. Okay. So in case of this diode, that instant could be omega t is equal to 0. So initial condition can be expressed as I naught is equal to 0 at omega t is equal to 0. I naught is equal to 0 at omega t is equal to 0. Therefore, by using the above equation, apply this initial condition. Left hand side we can take it is 0, right hand side Vm by omega L multiplied with minus cos 0 plus k, right? Therefore, from this we will get k value is equal to Vm by omega L. Then what you can do? Substitute k value into I naught equation. Substitute k value into I naught equation. Then what we will get? I naught is equal to Vm by omega L into minus cos omega t. This is the first term. Plus k value, that is Vm divided by omega L. Vm divided by omega L. Therefore, from this I naught can be expressed as Vm by omega L. If I take that as a common, I can write it as multiplied with 1 minus cos omega t. Multiplied with 1 minus cos omega t. Okay. This is the expression for output current. That is the expression for output current, right? Now, if you compare with respect to resistive load, resistive load, what was I naught? We got Vm by R into sin omega t. Then we simply plotted sinusoidal waveform. But now I naught equation has different profile. Okay, so we need to calculate what is I naught value at the different instance. For example, if you take at omega t is equal to 0, what could be your I naught value? Cos 0 is 1, then I naught value will be 0. Suppose if we take omega t is equal to pi by 2, then I naught value, cos pi by 2 is 0, then I naught value you will get Vm by omega L. Okay, next. Yet omega t is equal to pi, then we will get I naught value is equal to 2 Vm by omega L. Okay. Therefore, what you can do, let us take all of these values in the waveform so that we will get output current waveform. How it is? Let us see. Yet I naught omega t is equal to 0, we got I naught value was 0 from the previous calculation. Yet omega t is equal to pi by 2, I naught value is Vm divided by omega L. Okay. Yet omega t is equal to pi, I naught value we will get 2 Vm by omega L. That is what we calculated. Okay. Now here important point is one basic question yourself. Can we join these 3 points by using a scale? Yes or no? Answer is no. Why? Suppose if you join these 3 points with the help of a scale, you will get a straight line, right? But equation is not in the form of y is equal to mx form. It is not a straight line equation. It is Vm by omega L, some number, doesn't matter, into 1 minus cos omega t behavior. So you should join these 3 points with a smooth curve. It looks like this. Okay, Vm by omega L multiplied with 1 minus cos omega t waveform will be like this. Okay, this is what Vm by omega L into 1 minus cos omega t waveform. Now, one important question here. In the previous circuit, resist to load, I naught was 0, yet omega t is equal to pi. Okay. But at this instant, if you observe carefully here, I naught value at omega t is equal to pi, it is not 0. It is 2 Vm by omega L. If you recollect from diode switch definition, okay, for diode to be considered as turn off switch, current should be having 0 crossing. So because of this finite value of current, you cannot consider diode as a turn off switch. Diode can be treated as turn off switch only at the instant this current reaches to 0. Now if you go back and recollect inductor properties. What was inductor property? Whenever dIL by dt is positive or voltage across inductor is positive, we concluded that inductor stores energy. Okay. Therefore, by using that statement, we can say here 0 to pi, rate of rise of inductor current is positive. In other words, I naught waveform or inductor current waveform is increasing behavior. Or if you look into voltage across inductor, this is in the positive side. Therefore, we can say from 0 to pi, inductor is storing energy. Who is supplying that energy to inductor? That is source. Source is supplying energy to inductor. But that current will reach us to 0 only when energy stored in the inductor is released. But there is no resistor in the circuit. We have not considered any resistor. That means there is no dissipating element. In such cases, even I told this point in the inductor class. Whenever there is no resistance in the circuit at all, what happens? Whatever the amount of energy that is stored in the inductor, that will send back to source itself. Okay. So now onwards, whenever you come across these two combinations, what is that? Pure sinusoidal source and pure inductor. Whenever you had this combination, concept is how much time inductor will store energy. It will take same time to release that energy. Releasing in the sense it will send back that energy to source itself. Now you tell me how much time inductor stores energy, that is from 0 to pi. Inductor stores energy from 0 to pi. Therefore, it requires energy to release. How much time it requires? Another pi interval it requires. That is from pi to 2 pi. Okay, that means whatever the rate of rise of inductor current, with the same rate that inductor current will decreases. Rate means what? When we changed the angle from 0 to pi by 2, the change in inductor current is Vm by omega L. When we are changing from pi by 2 to pi, the change in inductor current is another Vm by omega L. Therefore, but this change is in the increasing fashion. Therefore, in the negative half cycle of source voltage, when we are changing by another pi by 2, that means when you reach to 270 degree, this inductor current will reaches to Vm by omega L. Okay, the change will be Vm by omega L. Now that change is in the decreasing fashion. When we are changing by another 90 degree, this current will reaches to 0 because the change will be another Vm by omega L. Therefore, if you join these 3 points with a smooth curve, we will get output current waveform something like this. Now, observe very carefully here, what is inductor condition from 0 to 2 pi in one cycle? 0 to pi, it is a storing energy from source. Source is supplying that energy to it. Pi to 2 pi, inductor releases that energy. To whom? That is back to source. Okay. Now, one important, very important point here, 0 to 2 pi, throughout the cycle, current is in the positive half cycle only. Current is in the positive half cycle only. Suppose if I draw the direction of current in this circuit, that is I naught, it is always flowing in the one direction, that is from x to y. Okay, it is not changing the direction of current. Remember carefully here one valid question. When there is no change in the direction of the current, how can you say that inductor is sending back that energy to source? Okay, now there are two situations here. For example, if voltage is positive, current is negative, product is negative. If voltage is negative, current is positive, again the product is negative, right? Power is flowing back to source means either V naught or I naught can be negative. Both not necessarily to be negative. Okay. So in rectifier circuits, remember in rectifier circuits, entire rectifier circuits, negative load current is not possible. Why? Because in rectifier circuits we will use either diode or SCR. They are unidirectional switches from switches class. Okay, they cannot carry the negative current. We are neglecting reverse recovery currents. Reverse recovery currents are not in the discussion at all. Therefore, negative current is not possible. Okay, but power direction is negative means it is possible with the negative voltage, right? So throughout the cycle from 0 to 2 pi, as diode is in conduction, or diode is carrying that load current, what is the point here? This pi to 2 pi, as diode is in conduction, negative half cycle will appear across the load. Negative half cycle will appear across the load. So in this waveform, if you observe carefully, positive area and negative area are equal. Now observe very carefully here, if you look back into our basic rectifier definition, we told that rectifier circuit will transfer or convert AC power to DC power, whose average output voltage is finite value. But that statement is not valid here. Why? Because of pure inductive load, the average output voltage is 0. That earlier statement was applicable for all loads except pure inductive load. Okay. So positive area and negative area are equal. What do you mean by that? Positive volt second is equal to negative volt second if you measure x-axis in millisecond or second, right? Therefore, whenever the load is pure inductor, average output voltage is 0 according to volt second balance concept. Otherwise, circuit will damage. Okay. Now, From now at this instant at 2 pi, this current reaches to 0. Therefore, we may think that diode may turn off at the instant 2 pi, but immediately after 2 pi, the next cycle is starting, because this is all periodic cycles. Okay. Therefore, there is no time for diode to turn off. Whenever the load is pure inductive load, strictly speaking, pure inductive load is not possible. It is a hypothetical load. This is just for analysis purpose. But if you take RLE load at the first step itself, difficult to understand. Therefore, pure inductive load will give you a basic idea of this inductor concept. Slowly we will add one by one non-ideal components. Okay. If at all pure inductive load is there, diode will be in conduction in the entire cycle. Okay. Therefore, I can treat here 0 to 2 pi will be the conduction angle for diode. Will be the conduction angle for a diode, and I naught will be maximum at omega t is equal to pi. Okay. Whereas in our earlier resistive load, I naught was maximum at omega t is equal to pi by 2. Okay. Now one more waveform here, that is voltage across diode. That is voltage across a diode. So as diode is in conduction in the entire cycle, diode is in conduction in the entire cycle, voltage across diode waveform is 0 throughout the cycle. Okay, throughout the cycle. Therefore, Vd is equal to 0. Therefore, Vd is equal to 0. Right. Now let us note down these conclusions. What is that? Conduction angle for a diode is equal to 2 pi. This is important objective question. In fact, this question asked in one GATE exam also. Next, I naught is maximum. I naught is maximum at omega t is equal to pi. Okay. Next, if you look into average output voltage because of pure inductor, we can write average output voltage is equal to 0. This is as per volt second balance. This is as per volt second balance. Now in our earlier resistive load, we wrote I naught is equal to V naught by some number. Isn't it? V naught by R in the resistive load. Now in this particular circuit, can we write I naught is equal to V naught by some number? Answer is no. Why? Because average output voltage is 0, but if you look into output current waveform, area under this waveform is not 0. So whenever you get that type of ambiguity, always depend on the waveform. Don't follow the mathematical formulas blindly. Don't try to mug up these formulas. Okay. Understand the waveform clearly. Draw waveform with your own hand, even though lecture notes is provided. Then only you will understand the subject basic concepts. Okay. So now we have a contradiction. Average output voltage is 0, but average output current you cannot express it as V naught by some number. Whenever you have that type of discrepancies, you should always depend on the waveform approach. Okay. So now let us calculate average output current. What is the periodicity of I naught waveform? 2 pi. So 1 by 2 pi. What are the limits for integration? Integral 0 to 2 pi. And what is I naught equation? This was I naught equation. Vm by omega L multiplied with 1 minus cos omega t d omega t. Now let us simplify this integration. 1 by 2 pi multiplied with Vm by omega L Integration for 1 is omega t. For cos omega t, integration is sin omega t. Limits are from 0 to 2 pi. Now sin 2 pi is 0, sin 0 is also 0. If you apply the limits for omega t, you will get 2 pi minus 0. That 2 pi and this 2 pi will get cancelled out. Therefore, I naught, what is I naught? Capital I naught means average output current is equal to Vm by omega L. Vm by omega L. Now, one important point, take these two integrations. Observe carefully. Generally, this is one confusion in the students. Okay. Here, generally people used to ask, sir, here you wrote integration in terms of dt, and here you wrote integration in terms of d omega t. Where should we use integration dt and d omega t? Remember carefully. In this particular integration, I am solving differential equation. Whenever you are solving the differential equation, your integration variable is with respect to time. Okay. Next, what is the concept in this integration? What is the concept here? You are calculating average value. What is average value? Basically, it is nothing but area under the waveform. Okay. It is nothing but area under the waveform. Whenever you are calculating area under a waveform, integration variable should be with respect to x-axis. Don't blindly fix your mind that omega t. Integration is with respect to x-axis. Okay. So if you take x-axis in time scale, then you can integrate with respect to dt. If you take x-axis in omega t scale, integration with respect to omega t, d omega t. In case of dt integration, one cycle time could be 0 to capital T. In case of integration with respect to omega t, one cycle time will be 0 to 2 pi. That is why Fourier series also you should take the integration variable accordingly. Okay. So thumb rule is, whenever you are solving the differential equations, your integration is in terms of dt. Whenever you are finding the average values, integration is in terms of x-axis, no matter what is the variable on the x-axis. It can be time, or it can be omega t, or it can be theta also. Okay, sometimes they can be represented with a theta also. When you are calculating mean value or mean square value, that means average and RMS value calculation, integration variable should be in terms of x-axis. Okay, therefore here we got average value Vm by omega L. Now let us represent this average value on the waveform. So here, this is what average value Vm by omega L. So I can draw here one horizontal line whose magnitude I can represent with a capital I naught. Okay. Now I can compare this capital I naught with respect to peak value of I naught waveform. I can say this is IOP, small I suffix O and P. Okay, so small I naught is nothing but instantaneous value, that is a peak instantaneous value, I can say, right? So what is the relation between these two variables? Average output current is half of the peak instantaneous value. Therefore I can write like this, IOP divided by 2. Now you can put it in one box. We can put this in one box. Okay, this is about pure inductor half wave uncontrolled rectifier analysis. Now by taking this circuit, let us do one example. Now here the question is just our previous circuit only. I have redrawn sinusoidal source, diode, inductor. Okay, one ammeter is placed here in the series, so it will measure current flowing through load or the circuit. One voltmeter is placed across diode, one voltmeter is placed across inductor. Now the question here is, we need to write down the expressions. Okay, if the meters are MC type and MI type. Suppose I will do this problem in general with the symbols. by giving some values, numerical values, it is expected you to calculate according to that formulas. Okay. So what is the basic concept here? MC instrument means it will measure average value. MI instrument means it will measure RMS value. Okay. Therefore, the question is indirectly I am asking you to calculate, find average and RMS voltage across inductor and diode, average and RMS current flowing through the circuit, simple way. Okay. So as V1 is connected across inductor, average value, what is the average value? That is 0. Why? Because it is having full sinusoidal waveform. Average value, positive area and negative area will be 0. Now MI means RMS value. What is the RMS value for full sinusoidal? Peak value by root 2. Vm by root 2. Next, V2, as the second voltmeter is connected across the diode and diode is always in conduction, we will get voltage across the diode is equal to 0. Okay. Next, what about MI instrument? This will also measure 0 because diode is always in conduction. Across the voltage, whether it is average or RMS value, is always 0. Now coming to ammeter average value, just now we calculated, it was Vm by omega L. It was Vm by omega L. Okay. Now we want to write expression for RMS current. Before that, let me give you a small example. For example, I have a function x is equal to 5 minus 5 cos omega t, that is the function. I want to know what is RMS value for this function. How to write? I can write it like this: 5 square plus 5 by root 2 whole square total under root. 5 square plus 5 by root 2 whole square, this total under root. Therefore, if I take out 5 square outside the root, I will get 5 multiplied with 1 plus 1 by 2 is equal to root of 3 by 2. Okay. So 5 into root of 3 by 2. How, in what way this equation is related to our discussion? What is the expression for our current equation? I can write it like this: Vm by omega L minus Vm by omega L into cos omega t. Okay. So what is the basic idea here? Compare these two equations. In place of Vm by omega L, earlier we had 5. Therefore, IORMS, how can you write? Vm by omega L multiplied with root of 3 by 2. Okay. Where Vm by omega L value is nothing but average value. Root of 3 by 2 value, if you calculate, you will get 1.225. Okay. So these are the values you have to write in this place. Okay. You have to write in this place. So RMS value of the current waveform is equal to 1.225 times of average value. Now let us take third case, that is inductive load. Of course, earlier also inductive load, but that was pure inductor. I told that pure inductor is not available. Now let us take one of the non-ideality, that is the internal resistance, or you can also take external load resistance. All together is represented with some resistance symbol R. So in this case, again, source voltage is sinusoidal waveform. Vs is equal to Vm sin omega t. Source terminals are represented with A and B. Load terminals are X and Y. voltage across resistor here, voltage across inductor here. But what is output voltage? That is combination of VR and VL, that is measured across X and Y. Here X is with respect to Y. Load voltage is measured, X is with respect to Y. Now output current can be represented with a symbol I0. Voltage across diode denoted with the symbol VD. In this case, again source voltage is pure sinusoidal, device is a diode. Therefore, from 0 to pi, whenever the source voltage is positive, diode will be forward biased. Then what will happen? It will turn on. Voltage drop across the diode is 0. In that case, load terminal X will be connected to source terminal A. Therefore, voltage across XY terminal will be same as AB terminal. Okay, so throughout this course, you just follow these names. Okay, don't give plus minus polarity and change it and don't confuse like that. It is always preferable to give component references AB and XY. When diode is on, XY is simply connected to AB. Hence, voltage across XY will be same as voltage across AB. Therefore, I am plotting that. Output voltage will be same as source voltage from 0 to pi. And hence, peak value will be same as that of source voltage. The next waveform is output current. Next waveform is a output current. Now, when the diode is on, just now we told that voltage across XY is same as AB. How can you write voltage across XY? Voltage across resistor R into I naught plus voltage across inductor L into di by dt. That summation is equal to Vm sin omega t. Let us write down here. When diode is on, voltage across XY terminals R into I naught plus L into di naught by dt is equal to Vm sin omega t. This equation I can rewrite it as di by dt plus R by L into I naught is equal to Vm by L sin omega t. Okay. So observe carefully here. In our previous two cases, in case of resist to load, we had R into I naught is equal to Vm sin omega t. In case of pure inductive load, L into di naught by dt is equal to Vm sin omega t. But now, in this case, it is a combination of those two. Okay. So straight away, you cannot draw output current waveform until unless you know the equation for this differential equation solution. Now, just to get or to solve this equation, let us follow the standard procedure. Now, I can compare this equation, okay, with respect to the standard, okay, let us say this is equation number 1, okay, that is equation number 1, just to avoid a confusion. Standard first order linear differential equation. It is in the form of dy by dx plus py is equal to q. Compare term by term. Okay, compare term by term. So this equation is called first order linear differential equation, standard form. Okay, and this equation is also called Leibniz equation. Okay, this equation is also called Leibniz equation. How can we solve this equation? The first step is we should find integrating factor. E power integral p dx. Okay. Now after that we can write down the solution as, okay, we can write down the solution as y multiplied with integrating factor is equal to integral q multiplied with integrating factor, integration with respect to x plus k, okay, plus k. Now this particular is from mathematics point of view. Now we will use this conclusion to solve our equation number 1. Now by comparing term by term, let us find integrating factor for our first equation. What you will get? E power integral p. In place of p, what is the term you have? R by L. Therefore R by L, now integration is with respect to time, okay. Therefore we will get e power RT by L, okay, e power RT by L. Now after that let us write down solution. After that let us write down a solution. So what is the function we are interested to find out? That is I naught. In our standard mathematical form that was y. Therefore I can write it like this: I naught multiplied with if, that is e power RT by L, is equal to right hand side integral q place, what is the term I have? Vm by L sin omega t. Q is to be multiplied with if, that is e power RT by L. Integrating is with respect to time, dt, plus k, okay, integrating with respect to time, that is plus k, right. Now let us consider this is equation number 2. Now if you observe carefully here, in the right hand side, this particular integration is in the form of, again I am little bit deviating from our power electronics, I am looking into little bit mathematical conclusion. What is that? Integral e power ax sin bx dx. I hope you might studied this type of integrals in your plus 2 level, okay. Integration by parts, how to find out that? E power ax divided by a square plus b square, a sin bx minus b cos bx, okay. So from the mathematics point of view you can leave it like that, but in our subject we are interested in writing in the form of some number multiplied with sine of some angle, okay. Therefore let us rewrite this particular function: e power ax divided by a square plus b square multiplied with, I would like to divide a by under root a square plus b square sin bx minus b by under root a square plus b square cos bx. What should I do here? For mathematical adjustment, I should multiply with root of a square plus b square, okay. So what is the reason in writing like this? This particular term I can call it as cos phi. This particular term I would like to call it as sin phi, right. Therefore now you can just you can simplify the value inside the bracket as sin A cos B minus cos B sin A. And what is further simplification here? E power ax divided by root of a square plus b square multiplied with sin of bx minus phi. What is phi here? Where phi is equal to tan inverse sin phi by cos phi. So we can write it as b by a. Okay, we can write it as a b by a. This is also mathematical conclusions. Now I would like to use this mathematical conclusion for our equation. Now I will use these conclusions in order to simplify equation number 2. How to write down that? So that can be written as, now I am continuing from equation number 2. I naught multiplied with e power RT by L is equal to, now this particular term I can simplify by using this mathematical conclusion. What is that? Vm by L multiplied with e power ax, that is nothing but e power RT by L, denominator root of a square plus b square. Okay, when you are doing this comparison, I can say that a is equal to r by L and b is equal to omega. A is equal to r by L and b is equal to omega. So a square r by L whole square plus b square omega square multiplied with sin of bx omega t minus phi. Okay, minus phi plus integration constant k. So this is what the solution is, but we are interested in expression for I naught. We don't want I naught is to be multiplied by some number. Then what should I do? Whatever number you don't want, remove that by dividing both sides of the equation with that particular number. Therefore, by dividing both sides with this value, we will get left hand side I naught, right hand side Vm divided by under root r square plus omega L whole square multiplied with sin of omega t minus phi. Okay, Vm by root of r square plus omega L whole square multiplied with sin of omega t minus phi plus k into e power minus rt by L plus k into e power minus rt by L. Let me call this is equation number 3. This is equation number 3. Now can you tell me, is this equation number 3 is the final solution? Mostly we reached the final solution with one unknown here, k. K is unknown. From where you got this k? From integration. Okay, so k value is to be determined by using initial condition. What is initial condition? What is initial condition? That is I naught is equal to 0 yet omega t is equal to 0 because of the diode. Therefore, if you substitute this initial condition, we will get left hand side is equal to 0 and right hand side it will give you Vm divided by root of r square plus omega L whole square multiplied with sin of minus phi plus k into e raised to 0 plus k into e raised to 0. Therefore, we will get k value is equal to Vm by root of r square plus omega L whole square multiplied with sin phi. Okay, multiplied with sin phi. Now substitute k value into I naught equation. Okay, I naught equation, that is equation number 3. I naught equation, that is equation number 3. Therefore finally what you will get, I naught is equal to Vm divided by root of r square plus omega L whole square multiplied with sin of omega t minus phi plus again you have this term. Okay, therefore I can take that term outside, so let us take common plus sin phi multiplied with e power minus RT by L. So this is the final solution for output current. Okay, we need to draw waveform for output current based on this equation. Okay, based on this equation. Try to digest this equation. Equation number 4, right? We need to draw this particular wave equation as a waveform for output current. Now before drawing output current waveform, first let us try to understand what is the behavior of this equation number 4. Now observe carefully. If I give you one particular circuit, I will give you source voltage information, isn't it? Therefore Vm value is a fixed value. I will also give you that load parameters. What do you mean by that? R and L values are also fixed. Anyhow sinusoidal source frequency is 50 Hz. So omega will be 100 pi. The point here is Vm, R, L and omega are fixed values, numbers. Therefore if I substitute the given data, I will get one number here. Number will not influence the waveform shape. Please remember, number will not influence the waveform shape. It may influence the peak values. Okay, now what is the variable here? What is the variable? Sin of omega t minus phi. Right, sin of omega t minus phi. Even phi is also a constant. Why? What is phi here? What is phi here? Where phi is equal to tan inverse b by a, where b is equal to omega, a is equal to r by L. Therefore tan inverse omega L by r. For the given load, inductor, load resistance, inductor and source frequency, phi value is also fixed value. Therefore here variable is omega t. T is variable. Okay, that means this particular term will decide waveform shape. So what I can write here, I naught consists of first one sinusoidal term. Okay, I naught consists of sinusoidal term. Then what is the second term? Sin phi is a constant, no need to worry about this number. Exponentially decaying component, e power minus t into some number. So we can write it like this, exponentially decaying component. Okay, exponentially decaying component. Therefore before going to the waveform, what is the point you should have in your mind? Output current, when the load is RL nature, contains, there are two major components which will decide the waveform shape. What are those two major components? One is a sinusoidal and another is a exponentially decaying component. One is a sinusoidal and other is a exponentially decaying component. Okay, therefore we will draw such waveform. Okay, now in order to draw output current, I just rewrite that equation number 4 here just for reference. As we told, it has two components. One is a sinusoidal and another is exponentially decaying component. Okay, so if you select one particular value of omega t means what? It is some angle either in theta or sorry, either in degree or radian. By taking that angle here and substitute in this equation, calculate it, you will get one number. Okay, take that number here. Similarly, take another angle of omega t and substitute in that, find out, you will get some value, right? So if you are doing and joining all of these points, combination of sinusoidal and exponentially decaying component, it looks like this. Combination of sinusoidal and exponentially decaying component waveform will be like this. Now one question we need to understand here, that is, in case of resist to load, follow carefully, important waveform. In case of resist to load, I naught has peak value at omega t is equal to pi by 2. In case of pure inductive load, I naught has peak value at omega t is equal to pi. But here, where that I naught will have peak value. In order to understand that, we need to draw voltage across a resistor simultaneously. Okay, I will tell you what is the basic concept here. This particular waveform is voltage across resistor. This particular waveform is a voltage across a resistor. Now I want to know where exactly this output current waveform will have peak value. In order to understand that, suppose when diode is on, can I write equation like this? L into d I naught by dt is equal to source voltage minus voltage across resistor, right? Source voltage minus voltage across a resistor. Now if I do in this waveform, now just look back into this waveform. If I take different values of omega t and join all of the points, then you will get step by step output current waveform, something like this. Simultaneously, if you draw voltage across a resistor waveform, what is a voltage across resistor? R is a number, this number is multiplied with I naught value at every instant of omega t. I have I naught value at this point, this value is multiplied with R, so I will get one value here. Next omega t value, I will get I naught somewhere here, multiply that with the R. If you proceed in that way, you will get up to some angle of instant. Okay, just for reference, I will give one name for that. That is omega t1. So up to this omega t1, observe very carefully here. Source voltage, blue color sinusoidal, voltage across resistor, red color waveform. Okay, these two, if you compare, I can notice that red color waveform magnitude is below blue color sinusoidal waveform. What do you mean by that? Up to omega t1, I am writing here. Before omega t1, okay, before omega t1, I noticed here VR value is less than Vs. VR value is less than Vs. What do you mean by that? L into d I naught by dt is positive. L into d I naught by dt is a positive. That means inductor stores energy. Inductor stores energy. So current waveform will increase. Okay, current waveform will increase. So up to what instant this current waveform will increase? Now observe carefully here. Up to omega t1, as Vr is less than Vs, current is increasing. Current increase, it will reach to one particular value where Vr is numerically equal to Vs. Where Vr is numerically equal to Vs. If Vr is numerically equal to Vs, what do you mean by that? Yet omega t1 Vr is equal to Vs. Yet omega t1 Vr is equal to Vs. Therefore, from that equation I can write L into di naught by dt is equal to 0. Okay. Whenever the product of two terms is 0, we know that any one term is 0. But inductor is not 0 here. Inductor is not 0. Therefore, definitely di naught by dt is a 0. Recollect from the basics. When di by dt is 0, what do you mean by that? The function will have either maximum or minimum value. So, now again one more question, whether it is a maximum or minimum. Definitely it is a maximum. How do I know that? Before omega t1, inductor stores energy means current is in the rising fashion. Definitely it will reach us to maximum value. So, I can say here I naught is maximum or I naught value is peak value. Next, beyond omega t1, if you look into this waveform, I can notice that VR, red color waveform, is greater than blue color sinusoidal waveform. What do you mean by that? Voltage across resistor is more than the sinusoidal. Therefore, I can write here VR is greater than Vs. VR is greater than Vs. Okay. Therefore, what do you mean by that? L into di naught by dt is negative. L into di naught by dt is a negative. That is, inductor releases energy. Inductor releases energy. Inductor releases energy means what? Current will start to decrease. At some instant, current should reach us to 0. Yet what instant that current will reach us to 0? Whatever the amount of energy stored in inductor, it has to be released completely. At that instant, volt-second balance will satisfy. In order to know where that current reaches to 0, we should draw one more waveform, that is voltage across inductor. Observe carefully. I stopped I naught waveform at this point. There is a reason for that. I will tell you. I will complete. So from this discussion, we concluded that up to omega t1, voltage across inductor is a positive. Okay. So here waveform shape is not important. What is important for us? Area shown by this portion is important. Okay. Let me say this area is X. Now at omega t1, voltage across inductor is 0. That is what we discussed. Beyond omega t1, voltage across inductor is a negative. Okay. Let me shade this portion, and area of this portion is Y. Okay. So observe carefully here. Area of portion shown by shaded part X equal with area shown by shaded portion Y. Wherever these two areas are equal, what do you mean by that? Positive area, positive volt second, balances with negative volt second. At that instant, okay, energy stored in the inductor will be completely released. Okay. So at that instant, the current waveform will reach us to 0. Current waveform will reach us to 0. So the instant where volt second balance satisfies, at that instant current will reaches to 0. That instant is named as extinction angle, denoted with the symbol beta. Okay, so you can also say load current will extinguishes. Load current will extinguishes at the instant beta. At that instant, energy stored in the inductor is released. Okay, where volt second balance will satisfy. Right. So up to this instant beta, diode will be in conduction, because in the circuit diagram there is a path for diode current. Okay, that means there is a path for load current only through diode. So diode has to carry that load current. So as the load current is flowing, until the current reaches to 0, diode is carrying that. Therefore, until diode is in conduction, what is voltage across xy terminals? That is the same as source voltage AB. Okay, so up to beta, output voltage will be same as source voltage. So if you have a imagination here, blue color waveform is a sinusoidal. Okay, so from 0 to beta, just feel that you are taking the snapshot of that blue color sinusoidal and drawing here. The waveform will be looks like this. Okay, so at omega t is equal to beta, diode is turned off. Right, if you recollect diode switch definition, exactly this circuit only I took it. Okay, so this is what beta concept. Right, mathematical detailed mathematical explanation is just now we discussed. At this instant, as the diode is turned off, current will be 0 until devices start conduction again in the next cycle. Therefore, voltage across load is also 0. After 2 pi, again the same waveform will repeat. Again the same waveform will repeat. Okay, so the same waveform will continue. Therefore, in the output voltage side also, V0 waveform will be something like this. Okay, the same waveform will repeat periodically. What is another waveform we need to draw? See, let us complete inductor voltage waveform. After this beta, current is 0. Hence, don't forget, you have to close this with the x-axis. Okay, so that this voltage across inductor waveform is 0. Up to beta, diode is in conduction. After beta, diode is turned off. That means from beta to 2 pi, whatever source voltage is there, that source voltage now will appear across the diode. That source voltage will now appear across a diode. In this interval, the peak value here is Vm, that is same as the source voltage Vm. That is same as the source voltage Vm. So this is what waveforms for RL load. Okay, what are important takeaway from this particular waveform? Conduction angle is important. You have to measure conduction angle first, that is gamma d. Conduction angle, generally gamma d is after pi. Okay, what else? I0 is maximum at omega t1. Peak inverse voltage is equal to Vm. Okay, peak inverse voltage is equal to Vm. Now let us write down these conclusions at one place. Now the conclusions are: conduction angle for the diode is equal to beta. Okay, in this particular RL load, and I0 is maximum at omega t1, that is where VR is equal to Vs, wherever VR and Vs are numerically equal. Next, peak inverse voltage is equal to Vm. Peak inverse voltage is equal to Vm. Now let us define average output voltage, 1 by periodicity. If you look into output voltage waveform, in this waveform, I can notice here periodicity is 2 pi, that is for one cycle here, and the waveform is present from 0 to beta. Here there is one possibility for mistake. Students will write the limit as 0 to pi plus beta. If you write pi plus beta, it is wrong. Why? See here, when you are showing this angle as a pi means it is measuring from 0 to here. When you are showing angle here 2 pi means you are measuring from 0 to 2 pi here. Okay. So in the similar way, here I am writing beta. Beta means what? 0 to till this instant. So integration limit is 0 to beta, not 0 to pi plus beta. Okay. So let us write down here. Integral from 0 to beta Vm sin omega t d omega t. So it will give you Vm by 2 pi integration for sin omega t is minus cos omega t limits from 0 to beta. So if you substitute the limits, we will get V naught is equal to Vm by 2 pi multiplied with 1 minus cos beta. Vm by 2 pi multiplied with 1 minus cos beta. Okay, this is the expression for average output voltage. Now let us write down expression for average output current. Average output current can be written as I naught is equal to V naught by R. Here also there is one possibility for mistake. Suppose if you write down I naught is equal to V naught by Z, this is wrong. Okay, this is wrong. In your notes, write down and struck off so that you will not repeat this mistake again. What is the reason for that? See, load side is a DC. It is not good practice to use Z symbol. Okay, Z symbol means it is used for AC circuits, right? For example, if you write down output voltage equation, V naught is equal to R into I naught plus L into d I naught by dt. For this particular equation, convert each term into average terms. What you will get? Average output voltage capital V naught is equal to R multiplied with capital I naught. That is why I am telling, don't write symbols as per your wish. Each symbol has its own meaning. V naught is equal to R into I naught plus, now you tell me what is average value of LdI by dt, voltage across inductor, that is 0 according to volt second balance. Therefore you will get I naught is equal to V naught by R, not V naught by Z. Okay, this is about average output voltage and average output current expressions. Next, another important point here, we discussed output current waveform in this waveform beta concept by using volt second balance idea. But I want to get beta value exactly some number. What should I do? In order to get this beta, just one thought. I have I naught equation, which is equation number 4. In that equation number 4, can you tell me what is I naught value at beta? I naught value is 0. Therefore, in order to find beta, okay, in order to find beta, what you have to do? In equation number 4, substitute omega t is equal to beta and equate to 0. Okay, let us see how it is. Now, how to find beta? First, what you have to do, take output current equation. Okay, so what is that? Vm divided by root of R square plus omega L whole square multiplied with sine of omega t minus phi plus sine phi into e power minus RT by L, right? This is what I naught equation. Now what is I naught value yet omega t is equal to beta? I naught is equal to 0 yet omega t is equal to beta. Therefore, if you substitute that, left hand side is 0, right hand side Vm divided by root of r square plus omega L whole square multiplied with sine of beta minus phi plus sine phi into e power minus RT by L. Okay. Anyhow, the product of these two terms is 0. If you substitute Vm, R, omega and L, this number is a fixed value. Therefore, for this equation to satisfy, value inside this square bracket has to be 0. Then what you will get? Sine beta minus phi plus sine phi into e power minus RT by L is equal to 0. Okay. You cannot further simplify this equation. These type of equations are called transcendental equation. Okay. Transcendental equations. Such equations can be solved by numerical methods. Okay, numerical methods, right? So this is the way how to calculate beta value. Okay, so this is what RL load analysis. Till now we discussed three cases. One is resistive load, second one is RL load and pure inductive load. Of course, we discussed in the different order R, L and RL load. But let us summarize all of these results in this order. What are the important points for summary? First, let us look into average output voltage, that is equal to Vm by pi in case of resistive load. In case of RL load, V0, what was the result we got? Vm by 2 pi multiplied with 1 minus cos beta. In case of pure inductive load, we got that value as 0. Observe carefully, very important conclusions we will get. Next, average output current is equal to V0 by R, that is Vm by pi into R. In case of RL load, V0 by R, therefore V0 expression is this one divided by R, Vm by 2 pi R multiplied with 1 minus cos beta. Okay. Now coming to pure inductive load, what is the basic difference here? Average output voltage is 0, but average output current is Vm by omega L. Okay. Next, if we look into conduction angle of diode, okay, in case of resistive load, that conduction angle was phi, and in case of RL load, that is equal to beta, which was greater than pi, and for pure inductive load, this is equal to 2 pi. Okay. Next, another comparison is I naught is maximum at here omega t is equal to pi by 2 in case of resistive load, whereas in RL load this was maximum at omega t1. In pure inductive load, I naught was maximum at omega t is equal to pi. Okay. So this comparison table is important at this stage of analysis, right? Now after this comparison table, we can have one important conclusion. Now observe carefully. The first comparison is when load inductance is increases. Okay, first we considered load is a resistive load, then RL load, then pure inductive load. Now observe carefully, conduction angle was first pi, then greater than pi, finally is equal to 2 pi. 2 pi is the maximum conduction angle. Therefore, what we can say here, if load inductance, if load inductance increases, if load inductance increases, the first observation is conduction angle of the device. Okay, I can write like this, conduction angle gamma for device increases, conduction angle for the device increases, right? Next, if you look into output voltage, average output voltage, first it was Vm by pi, then Vm by 2 pi into 1 minus cos beta. If you compare these two values, we can say that second value will be less. Why? In case of RL load, you can refer the previous V0 waveform. Pi to beta, there was negative portion. Because of that negative portion, the net area under the waveform will reduce. Therefore, in these two values, second value will be less. Finally, when the load is increased to pure inductance, finally average output voltage is 0. So what we can say here, average output voltage decreases. Okay, in the rectifier circuits, if the load inductance increases, first comparison is conduction angle of the device increases, average output voltage will decrease. Okay, so at this stage we discussed for 3 loads on diode rectifier. So we will take more conditions and loads in the next lecture. With this, I will conclude this present lecture. Thank you.